Okay, so we'll start with this application of potentiometer. I mean, we have our potentiometer. We know how it works. What are the concepts involved? Now, where are we going to use the potentiometer for? What are we going to use the potentiometer for? So the first use of the potentiometer is the finding the unknown EMF. Let's say you have a cell. Okay, you have a cell and you don't know the EMF of the cell. Okay, let's say you have some cell around you and you just don't know the EMF of this cell. So this becomes an unknown EMF cell, a cell of unknown EMF. Now you can actually find its EMF by comparing this cell with another cell which the EMF you already know. For example, this EMF you already know 10 volt is there, and this EMF you don't know, the EMF. So you can compare both of them and you can find this value. Okay, so how to do that? Let's understand. Now, whenever you connect the potentiometer like this, now potentiometer and a cell like this, and then you take your jockey, and put the jockey somewhere on the wire. Now, when you put the jockey somewhere on the wire, what will happen that this ammeter is going to show you some reading. Okay, it may show you some reading. Reading means some deflection it is going to show you. Ammeter, some positive, negative deflection it will show you. If it does show a deflection, it means that there is a current which is flowing through this line. It means that there is some current which is flowing through this line. It also means that this EMF and the potential drop between these 2 points is not same. It is not same. We did this. This is the concept. Remember, this is what we discussed, that the current is not going to flow if this potential drop. Okay, if this potential drop here, let me just erase all this. If this potential drop is same as the potential drop across the cell. So if this EMF here, if this EMF is same as the potential drop across the resistor, then there is no current which is going to flow. This is what we understood as one of the concept of potentiometer. So here the same thing is happening, that here we see that if at all there is a current here, that this ammeter reading is there, some reading is there. What reading doesn't matter, but some reading is there. It means that there is a current flowing, and it means that this EMF is not equal to the potential drop across this length. Okay, now then what you have to do, you have to find something called a null point. What is a null point? By the name also you can figure out. The null point would be a point where the ammeter reading will become zero. That means you will take your jockey and you will find a point. Okay, you will find a point where you will find that this ammeter reading becomes zero. Zero means it is not showing any deflection. If it is not showing any deflection, then you can very well conclude that there is no current flowing here. Along this line, there is no current flowing. I is equal to 0. So this is your null point. So whenever you have a null point means that there is no current flowing through this circuit and the ammeter reading becomes 0. That's your null point. Now, what does it mean? We know that the potential drop across these 2 points, the potential drop across these 2 points, this potential drop, you see this potential drop is directly proportional to this length. This potential drop is directly proportional to the length. Now let's say you have found out the null point. You have found out the null point, and you have found out the null point to be at the, let's say, 60 centimeter. You have found out the null point to be at the 60 centimeter. That means the potential drop across this length of the wire is proportional to the length, it will be proportional to the 60 centimeter. Okay. That means the EMF of this cell is also the same. It is also proportional to the EMF of the cell would also be proportional to 60 centimeter. Now, mind it, this EMF was unknown. Remember, we discussed about the known unknown EMF. So we had one unknown EMF. This was our unknown EMF. Then you perform the same thing again. You perform the same thing again, but this time you change the cell. You put the new cell here. You put a new cell, and this cell, the EMF that is, this is a known cell. Okay, this is a known EMF. So this one previously you did not know. The previous cell you did not know. This you already know. Now this if you already know, and again what you do is to find a null point. Again you try to find a null point. So if you do find a null point, let's say at a certain distance here, you find a null point at a certain distance, and you find that this distance happens to be how much? This is 30 centimeter. So this is 30 centimeter. So again, for this cell also, you can make an equation that the EMF will be proportional to the 30 centimeter. But this EMF will be even the known one, and this the previous one was the unknown one. Okay. So the known EMF proportionality you know, and the unknown EMF proportionality you also know. Now this is the proportionality. That means there must be some constant here. Some K value should also be there. So that K value is actually that this value here. What is the K value here? This value. You see, the current flowing in both the cases were same. When you performed the same experiment with an unknown EMF, the current flowing through this circuit was same, because I did not change this cell. I did not change this resistance. So the current flowing through this red conductor here was same in both the cases. And as the current I is same in both the cases, and the resistivity of the wire is, because the wire is the same, this red wire is still the same. So I L A, this whole I rho A, this quantity is constant. This is not changing. And this is what becomes our K. This value becomes our K here. So the constant here is I rho by A, and we see that this quantity here remains same. This does not change. So then I can write my expression as E1 is equal to KL1 and E2 is equal to KL2. And then I can divide this and find an unknown value here. I can find E1 or E2 or L1 and L2. This is one of the use of potentiometer to find the unknown EMF. First, you put the unknown EMF, find the null point. Then you put the known EMF and then find the null point. The conditions for both the cases are still the same. The same current is flowing, the same wire is there, resistivity and area is still the same. So E will be proportional to L. So E1 will be proportional to L1, E2 proportional to L2, and you can then divide them and find the unknown value. This concept to understand this concept is easy, but when you go ahead and start solving numerical around it, then you will struggle here, because this is one of the this concept will have one of the very complex problems. Okay, so understand the whole concept, and the numericals we will discuss obviously. The next use of potentiometer, or next application of the potentiometer, is finding the internal resistance of a cell. Okay, so there is a cell, and we want to find the internal resistance of that cell. Now how to do this? See, previously your meter bridge was like this. So let's quickly draw the meter bridge. This is our meter bridge, and this is the 1 meter wire here on the bridge, and this is our driving cell. As I told you, driving cell is not that important. It just gives some current in the circuit. And this was our known EMF, unknown EMF things with a ammeter and all. Okay, this is what we were doing. Now, in this circuit, now I am going to do a bit of change. So how to find the internal resistance? First, what you have to do is you take the cell, take this cell EMF, and there is internal resistance inside it. This is what you want to measure. First you want to measure this. So what you do, first you find the null point. Okay, you find the null point for this condition. So when you find the null point, again your expression will be E1 will be is equal to KL1. This is what your expression is going to be. Then what you do is to connect this cell then what you do is to connect this cell with another resistance. Now look very closely how it is connected. So let's say you connect it with another resistance here, R. Okay. Now previously, once you followed the null point logic, when you found the null point for this condition, E1 is equal to KL1, this null point was found out under the condition where no current is flowing. Remember, I is equal to 0. I is equal to 0, no current is flowing, and the ammeter reading was also 0. When no current is flowing in the circuit, then you know from the previous concept that V is equal to E. And that is why I have written here E, because then the EMF of the cell was balancing this potential drop. The EMF of the cell was balancing this potential drop. But if now I connect another resistance here, then there will be some current which is going to flow in this circuit as well. In this circuit as well. Now, then the EMF will not be balancing this length of potential drop. The next time I find the null point, I will find that the null point has changed. Because previously, when no resistance was connected here, when no resistance was connected, there was no current flowing through the EMF, and the potential drop across the EMF was is equal to the EMF itself. Okay, so potential drop across the cell was EMF itself because no current was flowing. But now because you have installed another resistance here, so some current is flowing. And because some current is flowing, then the potential and the EMF will not be same. They will not be same. This you have done V is equal to E minus IR. You have done this before. So they are not going to same. And then this length of potential drop will be balanced by not the EMF, but the potential difference now. Potential difference or terminal potential of this cell. Why? Because now the terminal potential is balancing this length potential drop. Previously, the EMF was balancing because no current was flowing in the cell. But now, as because you have installed a resistance, some current is flowing, and the terminal potential is going to balance off this potential drop across this length. And that is why your next expression will become V is equal to KL2. Okay, V is equal to KL2. So V, for in the first case, E is equal to KL1, and in the second case, it will become V is equal to KL2, and then when you solve it, you will get this value for internal resistance. How? Look here. Now E is equal to I plus I into R plus R, that you already know, and terminal potential is equal to I into capital R only, external resistance, and then you can divide these two values. So what will you get? R plus R by R is equal to L1 by L2. Then you can rearrange the expression, and then after rearranging the expression, it will be like this. That final value will come to this small r, that is the internal resistance of the cell. Internal resistance of the cell, which cell? This cell. Internal resistance of this cell, okay, will be is equal to the external resistance that you have installed here. Okay, external resistance here into L1 minus L2 by L2. Very simple. Okay, so go through this derivation once again. This is one of your PU derivation, CBSE derivation as well, and this is a very important concept. You have 2-3 such questions coming in mains exam 2019 as well, F20. Okay, potentiometer, this kind of questions has been asked before. Now next is the superiority of potentiometer to a voltmeter. We have understood that voltmeter should an ideal voltmeter should have an infinite resistance, but that is not practically possible. It will have very high resistance, but not an infinite resistance. So a very small current will still flow through the voltmeter. Okay, very small current will still flow through the voltmeter, and the reading will not be accurate. The reading of the potential drop it wants to measure, it will not be accurate. But potentiometer is a null method device. You see, when you are finding the null point, you are finding the null point under the pretext that the current is equal to 0. That is, it is not drawing any current from the main circuit. At the null point, it does not draw any current from the cell, and thus there is no potential drop due to the internal resistance of the cell. It measures the potential drop in the open circuit, which is equal to the actual EMF of the cell. Okay, it is equal to the actual EMF of the. On the other hand, voltmeter draws a small current from the cell for its operation. So it measures the terminal potential of the potential difference in the closed circuit, which is less than the EMF of the cell. That is why potentiometer is preferred over a voltmeter for measuring the EMF of the cell. Then the next topic is sensitivity of a potentiometer. Okay, how potentiometer is sensitive, or how can you make a sensitive potentiometer? Okay, now sensitive means what? Sensitive means able to measure very small changes. Okay, sensitive means able to measure very small changes. That is, a potentiometer is sensitive if it is capable of measuring very small potential differences, then it is very sensitive. And it shows significant change in the balancing length for a small change in the potential difference being measured. So for example, let's say if there is a potentiometer 1 and there's a potentiometer 2, and this potentiometer is going to measure let's say 2 volt potential difference. Okay, it measures a 2 volt potential difference between the 2 point, and the balancing length happens to be 40 centimeter. So it measures 2 volt potential drop at a balancing length of 40 centimeter, but this potentiometer measures the 2 volt potential difference at a balancing length of 80 centimeter. Okay, that means this second potentiometer is more sensitive. You see, more sensitive. Why? Because it shows significant change in the balancing length for a small change in the potential difference being measured. Okay, so that is what your sensitivity of the potentiometer is. Depend upon the sensitivity of the potentiometer depends upon the potential gradient along the wire. Very important. So what does it depends upon? Potential gradient. Smaller the potential gradient, greater will be the sensitivity. Okay, smaller the potential gradient. That means, let's say if I say a potential gradient is 2 volt per centimeter for a potentiometer, and there's another potential gradient as let's say 0.2 volt per centimeter, so definitely this one will be more sensitive. It one will be more sensitive. Smaller the potential gradient, greater will be the sensitivity of the potentiometer. Now, for let's say if you have a potentiometer but it is not that sensitive, and you want to make it more sensitive, so how do you do? So like, you can increase the sensitivity of a potentiometer by, you can increase the by reducing the potential gradient. Just now we did this, understood that smaller the potential gradient, greater will be the sensitivity. So I can improve the sensitivity by decreasing the potential gradient, and this can be done in two different ways. How? For a given potential difference, the sensitivity can be increased by increasing the length of the potentiometer wire. So you see that diagram that I told you, that why that diagram is a bit scary. There are the 4 wires and 400 centimeter length, this diagram here. So what is the purpose of this diagram? If it is not not so student friendly, or it's a bit scary, the purpose of this diagram is that, you see, we have understood the whole of the concept only using this 100 centimeter length. Okay, only this part. But this is a very ideal good potentiometer, so it is, the length is large. Okay, the purpose of having this 400 centimeter of length is actually to improve the sensitivity. You see, by increasing the length of the potentiometer wire, if we increase the potentiometer wire length, it will become far more sensitive, because the potential gradient will decrease. Okay, you know, the potential gradient will be V by L. So if you increase this value here, this value will decrease and the sensitivity will increase. Then for a potentiometer wire, fixed length, okay, of the fixed length, so you cannot increase the length any further, the potential gradient can be decreased by reducing the current in the circuit with the help of a rheostat. You know what a rheostat is? Rheostat is a variable resistor. Variable resistor. Okay, so you can use a rheostat, and you can you can decrease this value. But how? Let's see in the circuit, you see this is a rheostat. So this diagram is now getting very clear that why this diagram is there in the first place. So this extra length of the wire is increasing the sensitivity, and this resistance here is also doing the same. It is decreasing the current in the circuit. Okay, it is, what is it doing? It decreases by reducing the current in the circuit by the help of the rheostat. Now, if you decrease the current in the circuit, you see, okay, this you decrease the current. So V is equal to IR, the potential gradient. Okay, think in the terms of this potential gradient, V by L. So you can increase this and decrease this, or you can simply decrease this and decrease this. Same idea. And V is equal to again IR. So you can basically decrease the current and also decrease the potential difference. Okay, so these two are very important point. Read this carefully.